Good morning and welcome to Friday of week 3 of your Physics 5 a day, and far from winding down for the weekend, we are building up here to a big weekend of waves revision. So it's double slits today and diffraction gratings tomorrow. So to start with, let's imagine I have a tank of water and I'm going to use my ruler and go like this with it to make straight wave fronts. Now imagine that I've taken a photo of the water tank from above, and these are the peaks of the waves. At that instant I took the photo, these are the peaks of the waves, and they're travelling this way. Now what happens if they meet a gap, a wall with a gap in it? Well, waves bend around corners. And so what you get is something like this. You can see that the bit in the middle there managed to come through quite straight, but at the corners it has curved around. Now if you're wondering why that happens, look up Huygens principle, but I'm not going to go into it now. The important thing for us here is that we can see that if we made that gap narrower, the straight section would get smaller, and so you can see how if we got it narrow enough, we'd end up with circular wave fronts coming out there. And so this is very important for us. If we want circular wave fronts coming out, we need the gap to be about the same size as the wavelength of the wave. So if we send our wave towards two slits that are about the same size as the wavelength, we're going to end up with two circular wave fronts. So it's now as though I had two wave sources here. And importantly, these waves have the same wavelength, the same frequency, and if I choose anywhere I like, so let's say here, both waves are going to arrive at this point, and the phase difference between those two waves arriving at this point will always be the same. So wherever you are over here, these two waves will have a constant phase difference. Now imagine a little bit later these waves have continued moving and they've reached a screen over here. At this point, which is directly between the two wave sources, the two waves will have travelled exactly the same distance and will have arrived exactly in phase. So wherever they are in their cycle, they're always at the same point in their cycle. So that means they're always going to add up to a bigger amplitude than each of them had on their own. This is called constructive interference, and it means that the amplitude here is always going to be the maximum. So if this was waves in a pool, if this was two wave machines and you were there, you'd be going all the way up as high as both of these two waves added together, and then all the way down to as low as both of those two troughs together, up and down, up and down. So that's the best place to be in the wave pool. And so unsurprisingly, that's called a maximum. And because it's in the middle, it's called the central maximum. Now, if we move this way, then now the wave coming from here has to travel further than the wave coming from there, and if we keep moving we'll reach the point where this one has had to go half a wavelength longer than that one. But that means that this wave is always half a wave behind that one, so whatever this one is, that one will be the opposite, and they will always cancel out. And so in fact here, if this was a water pool, wave pool, that you wouldn't move at all. If you were there, you wouldn't move at all, because the two waves arriving are exactly out of phase. And so this is called destructive interference, and this is a minimum. So there, best place to be in the wave pool, there, boring place to be in the wave pool. And then if you keep moving, of course, further and further to come from this one, and so you'll reach the point where this one has had to go a whole wavelength further than that one. So this one's now a whole wave behind that one. But that means that once again, they're in phase. So if this one's a peak, that one's a peak. If this one's a trough, that one's a trough. It's just a whole wave behind. And so this one, again, they're always in the same place. So they're always going to add up. Constructive interference, and we get another maximum. So again, good place to be in the wave pool. You're going to go very, very high and then very, very low, up and down. Now, of course, this pattern keeps repeating all the way along, and there's a mirror image on the other side. And so what you get is a series of maxima with minima in between, and then in there it's not a sharp cutoff, it's going gradually from maximum to minimum in that gap, and then minimum to maximum in that gap. And there's a formula that tells you how the sizes of all these things relate together. So lambda is the wavelength of the wave coming in here. A is the slit separation. So that's from the middle of one slit to the middle of the next slit. How big is that? Capital D is the slit to screen distance. So here's where the slits are and there's where the screen is. What's that perpendicular distance there? And then X is the fringe separation. So these maxima are often called, and minima are often called fringes. And if you go from the centre of one maximum to the centre of the next maximum, so I've drawn this wrongly, I do apologise. From the centre of one maximum to the centre of the next one, so that's a maximum, that's a maximum. There we go. From the centre of one maximum to the centre of the next maximum, that is the fringe separation X. Now the setup we've got here, drawn here, is, as I'm sure you know, the setup we use with light. So if you shine a light at these fringes, and we usually use a laser so that it's just the one colour, then the wave fronts are as though they were straight. Now you might be thinking, but surely a laser or a torch, surely the wave fronts coming out of that are circular. They are, but it's the laser or the torch is so far away that the circles are so big by the time they get to the slits that they're effectively straight when they hit the slits. So if you have a laser here, shining the laser light there, then what you're going to find on your screen is the maximum amplitude oscillations. Well, what's that in light terms? That's bright light. So the maximum are going to be bright lights. And the minimum, that means minimum or possibly no amplitude at all. And so that's going to be darkness. So your interference pattern, this is called your interference pattern, when you're using light, is going to be bright, dark, bright, dark, bright, dark, bright, dark. The next video will look at using this formula, but just before we move to that, we'll just discuss what happens if we don't use light that's all the same colour. Well, if we have light that's different colours, then that means we've got different wavelengths. And let's say we're going to use white light, so that's a continuous spectrum of all the colours. Now, what is that going to look like? Well, red light has the longest wavelength of visible light and blue has the shortest wavelength of visible light. So if we look at the formula, if we're keeping the slits the same distance apart and the distance d the same, then if you make lambda bigger, then x needs to get bigger. So for red light is going to have a bigger value of x than the blue light, and then all the other colours will be in between. So what does that mean? Well, that means that if this is the central fringe, everyone's going to get there the same. So all the colours will mix and that will be white still. But then the next maximum for red is going to be further out than the blue one. So if that's the red one and that's the blue one and all the other colours in between, we can get a little rainbow. So instead of just having one maximum there, we'll have a little rainbow which goes from red on the outside to blue on the inside, and then the next maximum will be the same. And on the other side, mirror image. So red has gone the most out, blue's on the inside. So red on the outside, little rainbow, blue on the inside.